This time we'll be looking at angular acceleration. We have treated motion on the straight line, and we treated acceleration in that regard. Now we're talking about angular acceleration. This is the case of a circular motion. And we define angular acceleration as the rate of change of angular velocity. Let's look at this. Assuming we have this type of motion, this is point A to B, and the distance covered here is S. I will have an angle theta. When a body is performing this type of motion, we talk about acceleration, and not just acceleration, angular acceleration at the rate of change of angular velocity. So if we have defined angular velocity, omega as theta all over t, then we can say that alpha, which is angular acceleration, is the w, the t. Just like we said in the case of linear motion, if there is no change in velocity, or if the rates of change of velocity with respect to time is constant, then acceleration becomes zero. It is also a similar thing here. If a body performing circular motion does not have a change in angular velocity, the angular acceleration becomes zero. So in that case, we can say that if there's a change in angular, velocity, then we can talk about average angular acceleration. So in this case, we can describe it as this omega 2 minus omega 1 all over t2 minus t1. So if we now talk about instantaneous angular acceleration, in that case, we can talk about instantaneous angular acceleration as this. Yes, we have a problem here. If a rotating disk changes its angular speed at the rate of 60 radians per second for 10 seconds, calculate its angular acceleration during this time. Okay, it is simple. The angular speed is given as 60 radians per second, and the time becomes 10 seconds. And we're asked to calculate the angular acceleration, which is given as the w, the t, which is equal to 60 all over 10, which is equal to 6 radians per second square. Remember, the unit of angular acceleration is radians per second square.